what I'm hoping you're about to see is a slideshow. Now, this is just a name that I put together. So what does it mean? The idea is that we should be able to figure out how to build expandable rotating space habitats. Why is that a good idea? Because to build a space habitat that gives you 1G, which keeps us all healthy, it has to be rather large radius. And it's just too expensive to try to build something like that all at once. And nature's answer to the problem is to start small and grow. So we thought we would like to try to do the same thing. And what is the value of it? Well, there's all kinds of things that you could do if we were able to build something like this. We could begin to have an arm of human civilization in space that wasn't limited by real estate costs, so to speak, because of the growth, which solves that. So this should be able to be driven by profit from the beginning. The space station that we have already, provides lots of facilities that people use and want to use. So we could do the same thing. And this gives you an idea of the sort of scale that I think we could get to for a comfortable 1G habitat. But the really good thing is that it can be, you can stop, you can wait till you're ready to grow and so on. So here's an analysis of the goals that we're trying to achieve. 1G at 2 RPM, a large open interior volume. This should be a place that's not just a habitat, it's actually habitable and should feel Earth-like if this is going to work. It needs to have access to zero-G facilities for industrial purposes in the center. It should be, as far as possible, run on sunlight the way the Earth is. And one interesting part about this is that the majority of the mass of the habitat is going to end up being shielding. And perhaps as high as 99% of it will be shielding in the end. And for that to be possible, we really have to have asteroid mining and lunar surface mining and so on. And this will actually provide an economic engine in partnership with the mining industry in space. So here, this is just a quick introduction. We got 3 concentric cylindrical structures. The one in the center is zero-G, it's not rotating. The middle one, which is green, is rotating, and the other one is rotating only very slowly, just for stability purposes. For that to happen, you've got to have bearings, which you can see here. And the outer one with between the habitable space and the shield has to be a sliding bearing. She'll come to that in a minute. I'm getting ahead of myself. Because we want to get all the sunlight inside that we can, the sidewalls have to be essentially made of glass. This is a very common raw material in space, but we will need to develop a production facility for high quality glass in bulk. That's something that I know we will have to do, but I haven't addressed it yet. But it's a kind of problem when you've got plenty of sunlight and you've got plenty of raw material. Ingenuity should be able to solve that. And the zero gravity may even help. At the bottom, we have a shield floor. Let's see, the membrane. Okay, potential candidates for membrane. We think probably UHMW, ultra-high molecular weight polyethylene. We'll see, but that seems to be the front runner right now. Okay, I'm just going to keep showing the pictures because it sort of explains itself as we go along. So on the top left, you see the size of the initial deployment, which might be enough to provide living facilities for half a dozen astronauts or something like that if you get it out right. And it actually ends up turning into this much larger structure, and I'm going to show you how that happens. That's where we're going, is the one on the right. And you get a large volume increase there. We will have approximately 12 radial growth steps and another 4 growth steps along the axial direction. I'm going to show you all of this. So again, as I said, sunlight has to drive this. We have to be able to support not only the interior, where you want to live, but also the food production, which means you're going to have two offset diurnal cycles like we do on Earth, daytime and nighttime, on the opposite sides of the planet down here. And here we will have to introduce the same idea, but through a switching mechanism. We want as much sunlight as possible, so we will use the traditional configuration where the habitat's axis is perpendicular to the plane of the ecliptic. And we will have two mirrors, not just one, because we need as much sunlight as we can get. So yeah, sharing the sunlight is really important. And it's going to get to the interior via the light shafts you can see here. And we will have a switching mechanism that I'll introduce you for that later on. The thing has to grow at the rim. Okay, it's basic. So we had to figure out, how you can set things up so that's possible. How does that drive the architecture? And you've got to have continuous access all the way around the rim for loading of materials. And you've still got to keep out the radiation and so on. So this drives the kind of configuration for the shield floor you see on the right here. And as I mentioned earlier, we're going to need a sliding bearing because the shield must grow first in order to make room for the habitat to grow. So that means you have to have a sliding bearing configuration. Okay, how would this actually work in terms of deployment? Possibly a new Glen. I mean, it just depends on what's available. But that will launch the initial inflatable starter habitat, which, as I showed you earlier, looks something like this. I'm going to introduce you to all the parts and the dimensions. You can see the size of a person in there. It's important to realize that we will not be rotating right away because there's a lot of construction that has to be done before you're ready to do that. The end walls are flexible and include cargo airlock doors shown in the orange color there. Blue stands for the transparent. And we have mitral trusses to stabilize the entire habitat against rotational twisting forces. And everything that a lot of the things you're going to need for the next edition end up being carried on the underside of your floor. Now, the shield will be, of course, made from material from asteroid mining, most likely. And start off about 0.5 meter thick, end up being about 5 meters thick. It's going to be a 3-layer shield because we need to use some water to drive down the amount of dangerous radiation that's coming in, and water is a very efficient shielding. I'm going to show you how that might work. I'm going to grow the shield because we won't start off with a full-size shield. We'll start off with something that's about 1/10 of the final thickness. So is everybody can see this okay? Okay. So outer 10% of regolith is like a meteor bumper, 20% will be water, and then the 70% on the inside will be regolith again. And the function of the water is to drop down the energy level of the incoming radiation so that it then will work with the regolith, won't cause too much secondary stuff. So here's how you can build a shield that can be expanded from the inside that has these capacities, these proportions. You build in a series of water bag layers that are not filled with water. And then when you're ready to do an expansion, you add material on the inside and you transfer the water from the outermost layer to the next one in, and you pump in more water. And you can, if you keep doing that, you can keep the same proportions of the sort of 10, 20, 70 thicknesses, but constantly be increasing the thickness of the shield overall. Now, when I did these slides, we thought we'd need 7 meters, but in fact, we think probably now we can get away with 5. But again, this is a work in progress. So going back, having explained that, that's what the shield is made of. The next thing would be to add some solar panels on the outside. And what we're doing right now, and we're going to do the first expansion, which is the prototype for all the subsequent expansions. You're going to split the inner floor there along the split line, and it will have built-in restraint cables, which will allow the end walls to open out sideways like that. So you've made the thing bigger just by controlling the expansion with coiled cables in the center. And we'll be using that over and over and over again with some modifications and more sophistication on it. So again, as I was mentioning earlier, the partnership with mining is crucial to the success of a project like this. Another interesting thing is that nitrogen may end up being a limiting factor because once the habitat gets really big, the volume of nitrogen gas inside is truly large. It goes up with the cube of the radius, of course. So we have some adaptive strategies to help deal with that. Okay, so we got inner airlocks added, and you can evacuate airlocks, and it looks like this. We're going to start building the shield. You need the end walls and the doors, loading decks for construction materials. And we're now, what you see at the top and bottom of the screen is we're beginning to set the spring points for the glass shield. And of course, we're going to always have to be adding solar panels everywhere. And also cooling panels, because shedding heat turns out to be a big driver of this as well. So now you've seen the first expansion sideways of the shield. And we're going to install now the deck extensions, which are the base for the magnet bearings for the sliding bearing that allows everything to grow. So in the red dotted line, you see a tensegrity transformable frame there, which can either be sloped inwards or outwards. We got cooling panels to transfer across the rotational interface. And just as a convention, we won't be showing all of, we won't be showing all of these cooling panels that are on the ceiling of each level of the habitat. We're just going to be showing them here now, but they will be there all the time. So these radiant cooling panels are basically like radiators in reverse, and they have to be able to transfer the heat out to the outside. Rail-mounted robotic arms, very important. Most of the work is going to be done by these moving and assembling stuff. So we remove the temporary tethers, like so, and we are now, I think, almost ready to start rotating. Let's see, yeah, axis of rotation. So here we go. So what is going to happen now is that we can rotate the interior. We can rotate the pressurized part of the design. For the time being, the outside shield will not be rotating, just for now. Now we see here we're adding the first of the glass side shield walls. And so this is, for the first time, you see basically all of the parts of the final design are starting to become manifest now. So notice that we had to do a lot of preliminary foundation work on the exterior structure before we can really start expanding the pressure hull any further than it is right now. But now we've done that work, we've got a basis on which we can roll. So that's how, see how the tensegrity bearings have reversed the direction of the slope. That's a key part of what allows this whole thing to grow. So now we're going to start building the shield floor. And I mentioned that it needs to have openings all the way around the circumference. So it's a continuous gateway on either side, and it still provides the shielding to the interior. You're going to have a system of rails that run on the inside of the glass walls to make everything grow the way it needs to. Now we can start to rotate the shield. Now I'm going to just do a little sidebar on how the shield floor expands. Basically, it's a series of overlapping plates. And we're looking at now in cross-section diagrammatically. In the center, you've got the pressure hull. And what we're going to do is, in the previous slide, I mentioned that there were a center floor and 2 side floors that are, so we're going to look at how those all overlap now. You can see the center floor is made of 6 overlapping sections. And then we're going to show the side floors on the outside there. So that's the sort of diagrammatic overlap between 2 systems. And because the floors have to expand, they have to be flexible so that the curvature can change. These floors will also be tensegrity structures, basically struts and cables suspending bags of shielding material, whether it's water or bag regolith. The whole floor system will be flexible and tied together by cables. So now you're seeing how that the outer floor can expand, and then you can make the inner floor expand and fill up the gaps that have opened. So that's basically how we're going to grow the shield floor. I'm going to go back to where we were. So the rail-mounted robot arms are what's going to allow us to add new floors to the pressure hull. And I'm going to just show you how this all works. So the continuous gateways around the edge allow you to load construction materials. The robot arms put them onto the floor that we're going to use as our construction platform. The cable panels and the cab panels for the floor will be, the new floor, the new pressure hull floor will be zipped together, tied together by cables in the circumferential direction. And when you're ready to go, you're going to use the rail-mounted robot arms to control them, and you start to cinch the panels together in the Z direction of the screen. And it rises up until it's in its intended design position, still held by the rail-mounted robot arms, and they will now spin up this new floor so it matches the rotation with the pressure hull that is rotating. And then the pressure hull will drop down its mitral trusses and grasp the new floor, and the robot's arms on either side will let go. And you've accomplished the most difficult part, which is adding a new floor to something that's already spinning. And then we zip down the pre-rolled window wall membranes, pressurize, and then we're going to, I'm going to start just only talking where I need to show something, which is a lot of the time, but so we're going to do a lateral growth of the shield, which allows the pressure hull to rotate. This is, I think, a little bit of an automated sequence here. So restraint cables on the inside have been switched to new positions. And the part of the new purpose is to keep the inner edges of the floors stiff. The floors are flexible, so they have to be kept in a constant tension. And we're going to do this again, I think. Yep. This is about where we start to have bio-based life support. Up until now, it'll have to be mechanical. And so we're expanding pressure again, adding another floor. Interestingly, up to this point, we've been growing very aggressively sideways from this very small seed, I should say. And at this point, we're going to find that we can't keep growing sideways so fast for the pressure hull, because we're going to start running into the shield wall. So we then start to grow only at a half step instead of a full width step. Now we're going to install some very important bearings in the middle, which will support the central zero-G facility, the mirror in the middle, which will give us industrial zero-G capacity. And you can see on the left a note about how we transfer waste heat out. It has to go out to the side of the habitat, because the floor, the bottom of the habitat, is constantly being used for construction. So all the waste heat has to, for the time being, has to go out the sidewalls where the sunlight is coming in. And this is how we think we can do that. In order to conserve the nitrogen, which the volume we mentioned was earlier was a problem, we probably have an interior pressure membrane, just so we don't get hammered by that too soon. And as you can see, we're now beginning to add the zero-G workshop in the middle, and you can start to see how things are taking shape. a second set of bearings in the middle so that it can be 0G rotating, not rotating, that is. I'm just going to take a quick drink of water if you don't mind. Hold on. Okay. Anyway, you're starting to get the idea of how this works. So I'm going to speed up the pace a little bit. We've now evacuated the center, so that it's, again, to conserve on the nitrogen. And this is going to be, you see how we're running into the width problem? That's just, so we have to transition away from where we're sort of doing a double width expansion at the interior to just a single expansion. And here we go. Okay, so that's the last double value axial expansion. From here on, we'll be going at a slightly more sedate pace on the axial growth. But at this point, we finally have sunlight coming in through the sidewalls because we've finally got enough clear from the central loading bays that we can start to have sunlight coming through the sidewalls. And so we have two new free-flying mirror reflectors, which will now grow with along with the habitat as we expand. Okay, so this is starting to be a routine growth process now. So I'm just going to keep clicking it forward so you can see how it grows. And you can see the 0G workspace in the center is also starting to get much bigger. So now these next 8 steps are pretty routine. So I'm just going to step through them. You can see, by the way, that we have some trees growing on the inside and crops, and so then basically the walls of the habitats are intended for life support primarily. Now, while we're in sort of radial growth mode, the people who are living here will have to sort of shack in with the plants and the crops and everything in the sidewalls. And so it'll be a little bit of a kind of you constantly have to be moving where you live, as each time you expand the radius, you're going to have to move house 1 floor down. I should just mention that just a little bit on the dimensions here. You see these inclined stacks of floors that are appearing on either side. There are 5 floors that each spaced apart by 4 meters. And the slope is actually given by the 3, 4, 5 triangle. So you've got 20 meters vertical, 25 meters, 20 meters vertical, 50 meters to the left or to the right, and then 25 meters along the slope of the surface. Okay. So I'm just going to keep moving this out until we get to the point where we have gotten out to 1G at 2 RPM is our goal. I should point out that at about 56 meters, you can get 1G at 4 RPM, and we will probably shoot to attain 1G at 4 RPM at that 56 meter radius so that we can get to 1G fairly quickly. I think to begin with, it'd be more like sort of when we're first rotating, I think we're going to have approximately lunar gravity on the, on the inner floors when we're first spinning. But we'd aim to get to 1G as soon as possible. And then from thereafter, we would simply reduce the rate of rotation with each addition in the radius. Okay. Starting to get big here. By the way, I think this is the first time I've showed this to anyone, so I hope you're enjoying the ride. You have to give me some feedback afterwards. Okay, now we're getting close to the point now where we're going to need to think about growing sideways. And here we are, in fact. So we're going to change the way we grow a little bit. Instead of adding outwards, we're going to add on the left and the right side, but the process is going to be very, very similar. Again, basically you're building an airlock on each side so that you can add material on the outside and then have it incorporate. So here's what we did was we rolled up the outer wall membrane, and we had, well, let me go back. If you look closely, just above the two red squares that represent construction material on the lowest floor, at the left and right, you can see a small blue circle. That's a rolled up pressure hull membrane. And what we do now is we roll it down and then roll up the outer one. So we're basically using an airlock metaphor here, except it's a continuous airlock all the way around the circumference, one on either side. So using this approach, we can modify our previous strategy and we add two new floor sections, one on either side. Again, using the robot arms that run on the rails on the inside of the glass shield wall. And so now we've added new floor space on either side. We just then roll down the previously rolled up windows, and Bob's your uncle, we're starting to go sideways. So we do this, and you can see always in all of these situations, the restraint cables between the inner floors, one floor up from the outer, from the floor. Those restraint cables at the ceiling level in the outer floor are crucial to having the expansion be controlled rather than explosive. So we're going to have some pretty fancy winch installations to make that work. But interestingly, the fact that we have a vacuum in the center, a vacuum volume in the center, I think will reduce the severity of that problem, the amount of stress, because the only net force that's pushing everything left and right is on the lower two floors. I think I'm correct in that. So anyway, here we go. I'm just going to do a couple more of these. One thing, you see the red squares at the bottom, those represent construction materials that are loaded into the habitat every time there is a growth step. So all these construction material red squares there came in through the left and right doors on top of the new floors that were being added. So that's how we get construction materials added from the inside. Okay, so now that construction material has been assembled into the ultimate, the goal, which is to have living space at 1G. We've now got enough apartment space and office space and mall space to support a population of perhaps as many as 8,000, and to feed them using the crop space on the left and the right in the walls. And we have a zero-G workshop that is hopefully going to make us money to keep the habitat rolling. So where are we going next? Yes. We're having a sidebar. Okay, so what's this about? You can see that there are what I call radial elevator cars, probably 6 on either side of the habitat, which are capable of going up and down, obviously, but also of exiting from the habitat as independent spacecraft, acting as shuttles. So you don't have to have large visiting spaceships trying to dock with this rotating structure. We can use the shuttles to take care of loading and unloading, like ships in large ships in the harbor. So now we're going to go back to the main thread again. Now that we've grown, hopefully we'd be able to find a reasonably inexpensive source of nitrogen, and we're able to dispense with the membranes on the inside and have a fully breathable interior, open interior space. And of course, we will recycle all those membranes. And it will look something like this. Now, up until now, we've been using the fins on the side walls the sort of teal-colored horizontal fins for all of the cooling. But with this, the arrival of a much larger population on the outer floor, we can take advantage of radial, what I call like a dorsal fin type radiator, because the floors, but the floor space between the shield floor and the pressure hull floor is no longer required for construction. So we can use it to transfer waste heat out. And so we will still be using the radiators on the side, but we'll be using those down the middle for the bulk of it. So I'm going to do a little discussion here of how we control light and how the interior landscape might be built. I'm just going to very quickly touch on a few points here. I'm sorry for the reading here, but up until this point, we have engineering studies in back of us, thanks to Texas A&M University. I should add that this work was supported by a NIAC Phase 2 grant from NASA with myself and TransAstra and Texas A&M University working together. But the design that you're seeing is essentially my design. Texas A&M did the engineering, and the materials and economic studies were done by TransAstra. So 90 acres of penthouse level, like a woodland park, like a wildlife park almost, you can think of it, on top of an urban indoor mall about the same area, underneath which are 5 stories of living space and commercial space and so on, with atriums providing light. All of the, well, we'll come to this in a minute, but I think pictures speak louder than words, so I'm going to skip through here. I'm just checking if there's anything I need to mention. Oh, yeah. What you're going to see is slightly departs from the engineering studies in some small details, but basically near the center, when you handle the hub a little bit differently, but it doesn't affect the validity of the argument. So now we're going to look at light. How do we control the sunlight to get what we want? Since the agricultural space and the habitable space need to share the sunlight, like I said before, we have to have an interlocking day and night cycle. So we need a switch mechanism so we can have day and night alternating like this. And so how are we going to do that? Well, I'm going to show you how I think that will be done. First of all, you can see the blue lines point to a series of rotating, like a level or blind type configuration, which is basically mirrors that can change their slope. So the sunlight can go directly into the crop space, or it can go into the interior space. And you notice that there are also shutter doors for the top 4 growth levels. Now, we're going to show in detail how that might work, because the shutter doors have to have a very sort of particular configuration if they're going to do the job of sending the sunlight up the pipe towards the interior. So let's take a closer look at that. During the daytime, obviously, for the crops, the shutters are going to be open like this. You can see on the right, the interior is in night. And when the reverse is true, the louvers at the bottom do the job. And then for the rest of it, you have to essentially use some prisms, some internally reflecting prisms, which I'm going to show you now. This is a blow up of 3 of them. You can see that we can arrange the interior surfaces of the prism so that all of the light ends up being turned and sort of together and pushed up the slope. So that it only has, I think, 1 bounce inside the shaft, off the shaft walls to get to the interior. Now, what are we doing now? This is how we might construct the landscape. I'm going to go to pictures here so that, one more thing. Yeah, we have 12 small hills in the floor, and each one of which has a small pond or tarn in the top, like in a crater. And we have a sort of a winding river. Not really a river, but it's about 10 meters wide and about 1 to 2 meters deep. And let's go to pictures. Okay, I'm going to spend a bit of time here. If it'll stay still for me. Okay. So what I want you to pay attention to is the floor of the habitat, first of all. You can see we've got these hills. There are 12 of them, little hilltops, and a river that sort of meanders between them. Underneath that, you can see we have an urban outdoor space, which is lit by the lowest level of the lighting ports, light coming in from the left in this case, and being reflected up in the way we just saw to the interior ceiling of the urban space. And you can see also that there are atriums so that the lower floors get their share of sunlight as well. On the sidewalls, you can see that we have a series of terraces, landscape terraces, which have bridges between one level and the next. And the reason they can do that is because the terraces themselves are not level. They go up and down sinusoidally. And so where the up point of the lower terrace meets the down point of the next terrace, you can have a bridge. So this allows you to walk from top to bottom or from bottom to top on each side of the landscape. And now we're getting close to the end. So I'm just going to give you a quick view of the whole thing. You can see the dorsal radiators here on the outside, which can grow incrementally, as the final growth in width of the ground floor of the habitat takes place. The radiators can grow too. And this is what it looks like from the outside. You can just see the trees through the windows, so to speak. And this habitat happens to be in the orbit between the Earth and the Moon. So that's it. That's my slideshow. Hang on.
Thanks very much. That was really good. There are some questions in the chat which I could ask.
Sure.
One from Max. He says, how much material is required to build that structure?
Well, obviously a lot is the answer. But the key point is that you can grow it in stages. And it's just you grow as quickly as you can afford to grow, or as slowly as you can afford to grow.
You don't have to have all the material inside. You can bring stuff in from the outside.
Oh, absolutely. Everything. There's two ways you can bring material in. The great bulk of material will come in through the rim of the shield floor, and because the great bulk of the material is what will be involved in construction of the rings and the expansion. But we would also, I think there will be ways to bring, well, like I showed that there are these inclined elevators that go up and down the side of the structure. So after it's all built, that's how bulk material would enter, is using those 6 elevators on either side. But for the construction of, for example, of the zero-G industrial space in the middle, all of that material will come through the docking ports at either center, on either side of the center.
Okay. Another question here from David Jenkins. What's the cost to build it?
Well, we did do a notional cost exercise. I think we figured it was somewhere between $500 billion and $1 trillion, something like that. But we also did a quick sum that suggests that if you sold apartments to the 1,000 richest individuals in the world, you might be able to build it that way too. So, I mean, the point is, what would something like this be used for? And the answer is there are a great many possible uses, all of which would probably overlap. But again, it's what we're proposing is not an end structure. We're proposing an evolutionary path by which you can build something, and you can build as much of it as you want or as you can afford to. One of the applications that has sprung to mind recently in discussions is that it might be a really cool idea to put one or more of these in orbit about Mars using the material from the moons for construction. And that way you could have a sort of safe house at Mars if we end up having a colony there. This might be a really cool adjunct or, accessory to that. Who knows how it would actually work out, but the point is the capability is a seductive, intriguing one, I think.
It looked like you had these really big mirrors sort of outside your structure, reflected light inside.
Yes.
How do you keep those, where they're supposed to be, and how?
Yes. Well, we stressed a little bit about that. At one point, we considered joining them to the structure, but it's not good structurally speaking. It's not a stable thing to do. It's just a bad idea. So they would be free-flying, and they would have to have their own station-keeping capability. One of the reasons I'm here talking to you guys is because to move anything of this sort of scale requires some unconventional propulsion systems. You think about it, you realize you've got to have something that doesn't depend on, blowing stuff out the back. That's just not going to work. It's just so. Yeah, I mean, these are big things. Big things. It's a big structure. But
Anthony, oh, sorry.
No, just that. I think it's not unfeasible if you approach it incrementally. Because then it's just a matter of history. Things grow; they take a certain amount of time to grow. Cities grow. It's just a capability. We're talking about a capability, a theoretical capability, which could be, like an engine, like a vehicle. You do what you want with it.
Anthony, it's George Hathaway here.
Hi, George.
You started off by saying that the first structure, the internal one, was going to be stationary, at least in rotation, with respect to the Earth. And then as you add on additional envelopes, you might say, you're going to cause a relative rotation between each of the succeeding two envelopes and the initial workshop, I guess. How are you maintaining the correct rotation? I did not see any station-keeping rockets.
No, you're right. I didn't talk about them, but we would need to have, I forget what they call these large sort of gyroscope-type devices would need to be scattered throughout the habitat to help, maintain the correct attitude and whatever rotation you want to have happen. Yes, that would have to be part of it. Does that answer your question?
Yeah,
or not really?
Thank you.
Okay. Any more questions? No, not hearing anything. And was there anything else that you had to discuss, Anthony? Sometimes I know you guys are keeping slides back in reserve in case important questions. So I'm just going to ask: do you have anything hidden away that you haven't shown us yet?
Well, I'm afraid I'm not terribly well prepared for that. I do have a couple of things, but I would have to root around to find them. I'm not sure if you guys would be patient enough for me to find them. But
Anthony?
Yeah.
The stability of the Stanford torus was called into question. Did you solve the Stanford torus problem of rotation in space?
You might have to describe that a little more thoroughly for me to be able to answer it.
I believe there was two problems. One was the precession in orbit.
I think that we have that one under control because our axis of rotation is perpendicular to the ecliptic. So we're not trying to maintain pointing at the sun that way. The way the O'Neill colonies, for example, had to be configured in pairs to handle the O'Neill wanted them to point at the sun axially instead of radially, so to speak. But we don't have that problem.
And Michelle Broyles asks, how large in diameter is the final structure?
Oh, yeah, that's a very good question. Well, for 2 RPM, 1G at 2 RPM, you've got a radius of 224 meters nominally, although exactly where that radius would be in the lower 6 floors is a matter for discussion. You know, I think that would be a decision that will be made evolutionarily, so to speak, by the people who are in occupation and running and, you know, owning it and so on. You could make it, you could stop at a smaller radius at a slightly faster rotation. You could build it larger if you wanted to, although this is probably the most economic. I mean, once you start building larger, the costs per square meter go up because the tension, the radial tension, the hoop tension rises as the radius rises. And so it gets more expensive to build. And one other point I should make is that you do have to choose a destination at some point, because once you start growing sideways, widening your floor, it becomes much difficult to stop that and then start growing radially again. It's harder. Not maybe impossible, but harder. So you have to have a certain amount of confidence about when you're going to decide to go sideways and stop growing radially.
If I understand the shielding, it's basically 7 feet of regolith with a water layer in between, roughly?
When we were thinking that we would end up with 5 meters of shielding might be enough. You know, once we are out in space and doing, you know, learning more, we can, you know, you can always change that parameter if you want to, but we would, sort of notional design is 5 meters thick, of which it's divided into 3 layers. The outer layer, in this case, would be a 0.5 meter thick of sort of impact shielding of regolith. Then you'd have 2 meters of water to do the bulk of the heavy lifting of reducing the energy incoming from the radiation. And then the final 70%, which is 3.5 meters, I think, would be regolith again.
So if you have the GCRs, the galactic cosmic rays,
yes,
are the ones that prevent us from going very far unless we go very quick in space.
Yes.
Have you done that calculation to reduce it to Earth levels?
Yes, we did do research on this. This was the part of the research done by Transastra. And we think that you can get down to a feasible, you know, a level of radiation shielding, which is livable with 5 meters, but, you know, it could be that it's 6 meters or, you know, that's a variable.
Are you using any magnetic fields either in or around this to provide shielding from the solar wind?
Yeah, it's an interesting question. Certainly no objection to it. We haven't planned on it. As you probably know, that's a subject that's sort of under investigation and, you know, still to be proven, I think, in practice. But I would have no objection to it if it works. But our goal was to try to just sort of pursue a relatively simple model and see what it could do. You know.
Well, It looks like the model addresses a lot of the structural issues and some of the basic radiation protection issues. What is it? How do you expect to power this whole thing?
I didn't talk about this, but looking at this picture, you can see that the outer surface of the shield floor is in fact covered with solar panels. Whether they would be enough, again, it's a subject for study, all on its own, and a lot depends on how you choose to live on the inside. But we set ourselves a sort of a notional goal of avoiding nuclear power, for example, and of seeing if we could do the whole thing on solar power. And again, those are decisions which, to some degree, could be evolutionary. You can learn as you go with something like this. And at one time I would remember thinking, well, we could have a small moon that orbited the habitat that contained a nuclear reactor if we wanted to. So I know it's an open question.
Thank you.
Sure.
Anyone else have any questions? Then thank you very much, Anthony. That was very interesting talk.
Oh, you're welcome.
By the way.
What?
Very, very nice pictures.
Oh, thank you. Thank you.
Very nicely presented.